Welcome back to the show that tells you you are a quantum computer with free will, collapsing your wave function mind into your favorite eigenvector. My name is Justin Riddle, and this is another episode of the Quantum Consciousness series. In today's episode, we'll be exploring Knightian Freedom, an idea put forth by Hartmut Neven in the context of quantum computers, which states that as you have a sufficiently large quantum computer, you're unable to compute what is going on internally, and this might give a little bit of wiggle room for free will to be taking effect. By the end of today's episode, we'll ask the question, do quantum computers have preferences, and can these preferences be exploited in next-generation artificial intelligence? This episode is available on YouTube, and an audio-only version is available on Spotify and Apple Podcast. If you like what you hear today, then please like this video, subscribe to this channel, leave a comment below, or for the audio listener, write a review.
Join me deep inside the mystery of numbers. Come and huff a metaphysical new. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
Alright, so today's episode I'll basically be exploring a paper that was put out by Hartmut Neven. He is at Google's Quantum AI group, and this paper is Do Robots Powered by a Quantum Processor Have the Freedom to Swerve? This was written along with Peter Reed and Tobias Rees, and this was put on the preprint server archive in 2021. I have not seen an updated version that went through peer review, so I think this is, to my knowledge, the final version of the paper. So to dive into this, the outline is I'm going to give a little bit of a brief primer on digital computers, quantum computers, to the degree that you need to understand the arguments put forth in this paper. And essentially, there are three different stages in this model. One is establishing the concept of Knightian freedom as kind of a way to explain free will. The second stage is building a quantum circuit that allows a quantum computer to express a preference. And the idea is that that preference being expressed in a quantum computer is its free will. And then a mechanism to leverage that preference and pair it with an artificial neural network as a way to sort of build a novel system which is going to have some essence of self-preservation while it is artificially simulating the environment. So a little bit wacky, pretty interesting. And then finally, I will end talking about quantum annealing and kind of questioning if this model really answers the questions that it sets out to answer. So to begin with, I'll give a brief introduction of digital and quantum computers. A digital computer is made out of bits. So these are stable binary states that are, called 0 and 1. But really, this can be any physical state that is going to be maintained through time. That is the foundation of a digital computer, the ability to store a physical state arbitrarily into the future and to maintain that sense of simple solidity where a 0 is a 0 and a 1 is a 1, and they maintain that state into the future. Then you add logic gates. These are systems of transformation where you have input bits being transformed into a output bit or multiple bits. And then by stringing together many of these truth tables, you form a digital algorithm. And these algorithms are a series of transformations that take place on a set of input bits to make them into some output bits. And then this forms the foundation of all the computations that you see around you. And so you start with these very simple components, but then you can scale it up, build more applications, and develop a lot of software, which gives us the fancy technology that you use today. So things to keep in mind about digital computers is that this is an entirely deterministic process. So if you have the inputs and you know what algorithm is being run, then you can generate those outputs universally, right? So Alan Turing defined a universal Turing machine. This is a deterministic system where all digital computers are functionally equivalent to each other and they can all process the same information in the same pattern. So a quantum computer is, instead of being made out of digital bits, it is made out of quantum bits or qubits. This is a wave function or a probability space that is superimposed on top of a 0 and a 1, where there is some probability of being in state 0 and a probability of being in state 1. And then the quantum bit enters into a superposition of uncertainty, as it can be in either 0 or 1 at a certain probability. And then the wave function is essentially those probabilities that are assigned. And as the wave function evolves through time, it can actually change what those probabilities are. And so the evolution of a quantum bit from the past into the future is deterministic. This is called unitary evolution according to the Schrödinger equation. And this evolution can be described entirely. And when you have multiple quantum bits interacting with each other in a quantum circuit, you can create logic gates similar to like we had in the digital computer example, except here the logic gates are acting on quantum bits and kind of manipulating the shared probabilities of these different quantum bits collectively. And so it doesn't matter how many quantum bits you have together, but as they evolve, they are going to deterministically evolve. And you could, in theory, calculate what the probabilities of these various quantum bits are going to be. The wild part is that you set up these quantum bits as digital bits, and then you evolve them into this quantum state using these quantum circuits. And then the wild part is that when you measure the quantum system, you're going to have a wave function with a different probability of receiving a number of different outputs. And then upon measurement, there is a collapse of the wave function, a reduction that takes place. And this space of all these possible futures gets smushed down and becomes one physical digital reality that actually takes place. And that process is non-deterministic. It is random. So that's enough to get us started today, and we're going to dive into the concept of free will and some of the challenges, and then we'll come back to quantum computers. So free will is the idea that we make choices in our lives. And the challenge with free will is that it's hard to define. We have an internal sense of having free will, but when you try to lock that sense of choice into anything in reality, it becomes very, very challenging. So some of the different options that we might have are determinism. In determinism, as you go from the past to the future, there's the laws of physics and they define this transformation. It is entirely knowable. There's no mystery. There's no magic. It's just, here's the starting place, here's the transformation rule, and then here's where you end up. And under determinism, it seems challenging to feel like that is free will, okay? Somehow being governed by the laws of physics, the laws of motion, it's not really what it seems to be making a free, conscious decision about your life. The alternative that we can think of is randomness. On one hand, we have determinism. On the other hand, we have random. And these are maybe antithetical to each other in some sense, and yet neither of them feel like free will. Neither of these gives us a sense of, okay, if I just chose randomly, now that is the sense of having a conscious choice. Now, Hartmut Neven starts off his paper by giving the example of a little girl, and she's asked, what ice cream flavor do you want to eat? And she says vanilla. And then the next time you ask her, she says vanilla. Then you ask her again, she says vanilla. And every time that she's given the option to pick an ice cream, she chooses the same exact choice. And then Hartmut Neven makes the argument that, well, she has a strong preference. And if you ask her, did you choose when you picked your ice cream flavor? She would say, yes, I chose vanilla. This is what I want to do. And so he makes the argument, maybe that is what determinism might actually be like in the real physical realm. Let's say we have some natural occurring system, and you measure it, you ask it a question, and maybe it always gives you the same answer. And so you would say that is a determined answer. But then maybe the alternative interpretation is that the system just has a preference. The system always chooses to move its particles according to the laws of motion. This is just what it wants to do. Its preference is Newtonian mechanics of motion. On the flip side, if you do not have a preference, so let's say the little girl is deciding what kind of soup she wants to eat, but she doesn't really have a mind for soup. She doesn't have a strong preference on soup, and so she chooses soup randomly when given 4 or 5 options. This would be the equivalent of a natural system that, under certain conditions, will give a random output. And so maybe the dichotomy between determinism and randomness is having a preference in determinism and not having a preference in randomness. And this is a little bit of a anthropomorphization, but maybe this is a way that you could choose to interpret what you are measuring in the world. Now, that is one of his arguments, and it's interesting. It's tough to combat, although it doesn't really give us anything new. It just kind of says we're going to reinterpret what we're seeing in the world in a different manner. But where I think he starts to get very novel is when he introduces this idea of Knightian freedom. So Knightian freedom, or Knightian uncertainty, is the idea that as you develop a sufficiently complex system, and in this case we're using a quantum computer, where as the quantum computer evolves, the number of states that we have to keep track of is exponentially related to the number of quantum bits. So if every quantum bit has 2 possible states, we have 10 quantum bits. That is 2 to the 10th power to describe the number of states that they occupy. Once we hit 100 quantum bits, now we have 2 to the 100th power to describe the system. And as we introduce more and more logic gates, the amount of transformations that we're going to have to keep track of in this massively large space also is increasing exponentially with each of these transformations. And so in order to calculate what are the resulting probabilities after a quantum system of 100 qubits goes through 1,000 quantum logic gates, the exponentially massive size of this system is so big that it could never be computed ever on any sort of device that we could build. So let's say we had a supercomputer the size of the universe, and it's a digital computer, and we're computing at the scale of Planck's scale. That entire universe-sized supercomputer operating at a very, very fast operations per second, even a computer that size could not compute 100 quantum bits moving through 1,000 quantum logic gates. And this is wild, and this is really capitalizing on our inability to really think about exponentials. And part of what makes quantum computers so powerful is that they're leveraging these exponentially large computational spaces with even just a handful of, 100 quantum bits. In the future, we're likely to see thousands of quantum bits, maybe millions of quantum bits, or billions, gigabytes of quantum bits. Once we start hitting those scales, we are even further into these astronomically large exponential spaces. And so not only can you not calculate this on a digital computer, but quantum computers fail to capture what is happening in other quantum computers. So there's this idea of quantum simulation where you can take a quantum computer and you could simulate a protein or a molecule, and the quantum computer just needs to be a few orders of magnitude bigger than the protein or the molecule. And that's fine and dandy, but we don't actually know what is the computation itself going on internally. We can't look into the quantum computer and see the details of that computation. We can simulate, and we can run multiple simulations and get a feeling, get some sense of the behavior of the protein or of the molecule. But we're not faithfully, reliably generating all of the data of that internal process that is taking place in that system. So we have the ability to simulate, but not to know. We cannot know what is happening inside of a quantum computer once it's sufficiently large. We cannot know what is going on in a quantum computer that is sufficiently large. We can simulate other systems, but there's a limit to what is knowable. So Hartmut Neven makes the appeal that because the system is reaching a point where we cannot, by definition, know what is occurring within the inner workings of a quantum computer that's even moderately sized, this gives us some wiggle room where maybe there's some additional extra sauce inside this quantum computer, and this might be something that is free will, something that goes beyond the typical laws of physics, something that is introduced beyond what we currently understand and know. So while this sounds a little bit hokey pokey, the question is there a way to test this concept? And I think this is where the paper really shines and where there's a very tangible component to what is being said. And I think once you hear of the experiment that Hartmut proposes, you'll get a better sense of why this might be interesting. All right, so here is the experiment. So essentially, there is an algorithm that you can run where the algorithm is going to generate a set of possible states at the exclusion of other states. So this is what is called a Dicke state, D-I-C-K-E, where essentially there's a set of options that the quantum computer could be in, and there's another set of options that it is unable to be in. However, within the state of options that it could be in, the algorithm is going to generate a uniform distribution where there is no actual preference for any particular state. It's just going to select a subset of options that you could be in, and then within those subsets of options, there is no preference, okay? So this is an algorithm that can actually be run on a real quantum computer. Now the question is, if we have the same quantum computer and we run this algorithm multiple times, are there any statistical regularities in the output? In other words, we've set up the system to have a uniform distribution, and yet the quantum system is going to express a non-uniform distribution. There's going to be some bias towards some states over others, some sort of preference, if you will, in the system itself. Now, this can actually be run. You can run a quantum computer many times, measure the outputs. There should be a uniform distribution, and if there's not, what is left to explain that? What is there in the system that could be manifesting some sort of preference over one state or another? Now, the challenge is that you need to rule out error, okay? And so in reality, when we run a quantum computation, we're running it in the physical world, in some room, in some building, in some location on the planet Earth. And we have electronics, we have physical, mechanical components, electrical engineering components, and all of these components are subject to error. And so the real challenge is going to be ruling out the error in the system as contributing to the bias, and then allowing for there to be some genuine preference by the quantum computer itself, just by virtue of its own inner workings. And that is maybe an insurmountable challenge. However, what if in the future we are able to achieve a near perfect quantum computational process, and then we have a level of specificity to investigate the question, is there some sort of freedom in the system to choose when there is no built-in preference towards one thing or another? All right, so from here, Hartmut takes it one step further. So he suggests, let's say that we do find a bias in the system, okay? Some sort of freedom to swerve, which is a reference to the ancient Greeks of the Epicurus lineage, which said that maybe atoms could deviate from deterministic physics and swerve out of alignment in their own free will way. Here, we're not quite swerving in the sense that we're violating any sort of law of physics, but here we're creating a situation where there's a uniform distribution of random choice, and then there's a bias nonetheless in the system upon measurement. So let's say that there is a quantum computer that exhibits a preference. This quantum computer prefers this one state over another. Hartmut then makes the kind of speculative jump that this is a happy state of the system, because when you exert a preference, you exert preferences towards things that you like, and this is a quantum computer liking something, and therefore when it exhibits choice that it wants, then it is in a state of happiness or some sort of positive valence. And so he's making the jump that we're going to now start assigning value and kind of subjective positive meaning to whatever that preference is, okay? And then we're going to take it another step. We're going to start tweaking the circuit. So we have a quantum circuit that generated this arbitrary choice state, and we're going to start altering that circuit to amplify the probability that the quantum computer is able to generate its preferred state. So we're going to start tweaking the circuit, trying different things. When we get less probability of ending up in that preferred happy state, then we undo that change. But when we make a change and there's a slightly higher probability of getting into the quote-unquote happy state, then we're going to keep that change and start making additional changes. And eventually, we are left with a weird random quantum circuit that generates a preferred state within the quantum computer. And then when you were asked, okay, well, what is this circuit doing? Your answer is it's aligning with the preference of the quantum computer itself. This is an algorithm for preference, or to make it a little more extreme, an algorithm of happiness for this very particular quantum computer. And if we had a different quantum computer, presumably it would develop a different preference for a different set of states, and the quantum circuit would end up looking a little bit different for that system versus another. And so to read a fun quote from this paper, performing this experiment is doable on Google quantum processors, which are approaching around 100 qubits. We suspect that most of our colleagues in the quantum computing community may consider performing this experiment not a good use of time, as they have confidence that the laws of quantum mechanics as stated today will prevail. But to our knowledge, high-fidelity experiments involving an effective Hilbert space of 2 to the 100th power, or 10 to the 30 dimensions, have never been performed. So it may be worth taking a closer look whether non-random deviations from the predicted uniformity are detectable in such large Hilbert spaces. Of course, additional structure not accounted for by the theoretical output state is likely to be present due to imperfect noisy hardware. The experimental challenge will be to demonstrate that such deviations from the prediction cannot be explained by noise in the quantum processor. So we already mentioned that a second ago. All right, so we have reached a point where we have developed a quantum circuit for happiness of this one particular quantum computer. It is essentially swerving from uniformity in some way, and we are magnifying and amplifying the swerve in this particular quantum computer. We've created the swerve circuit of sorts. And so step 2, as Hartmut and colleagues put it, is going to be generating error-correcting code oriented around creating the happy state in this happy quantum circuit. So this is a standard process in a lot of the quantum algorithms that are being developed, particularly the ones by IBM and Google, which do not rely on quantum annealing, but more on that later. And so what you can do is you can basically entangle additional quantum bits and measure those quantum bits and then understand what deviations in the quantum state are occurring. And then based on these error correcting measurements that you can make, these so-called parity measurements, you can then calculate what sort of gate manipulations you want to add into the circuit to then return that quantum system back towards that happy state. So in other words, there's some sort of happy state that we're moving the system towards in our quantum circuit, and we can detect deviations away from that state, and then we can correct those deviations and get us closer and closer towards that quantum state. And here, Hartmut and colleagues add some fun terminology. They refer to these parity measurements as interoception, which in psychology and physiology is understanding of one's own body. Interocepting. It's kind of like introspection, but internally into your physical body. And so they're making a bit of an analogy, saying that it's essentially the system self-measuring its own body, detecting deviations from its preferred state of being, and then applying these corrections upon itself to then reapproach that stable, happy state that it is trying to get back to. And here they make the analogy that this could be some form of fundamental homeostasis occurring not physiologically, but at a quantum computational level. So there is some quantum computational state that is preferred, and there's a way through error correction to maintain a preferred quantum computational state. And that feels like some sort of homeostasis as the system is trying to get back to its, balance point. And so we can think of error correction as a homeostatic force. And here is where they try to make the jump into psychology. Okay, so you're in your preferred happy state. Deviations from that happy state are by definition more negative. So as you move away from homeostasis, right, there's some electric fluctuation in the room causing a disturbance in your quantum computer. This feels bad. You're moving away from your preferred homeostatic state. And so all these deviations can kind of be defined as a negative valence form of expression. And so here Hartmut Neven gives a quote from Leo Tolstoy's opening line in the novel Anna Karenina. All happy families are alike. Each unhappy family is unhappy in its own way. In other words, there is only one way to be happy, that is homeostasis, and all other deviations from that stable happy state can be defined as different forms of unhappiness. So this next part is very speculative, but I think it's kind of fun and interesting. So as we are running the happy circuit and performing error correction upon it, we're going to start to document and keep a log of all of these different errors which have taken place. What we're going to do is we're going to keep track of the similarity relative to each other and relative to our happy state of each of these various different errors. And we're going to now look for statistical regularities in the structure of errors that occur surrounding the happy state. So there's kind of a concentric circle where as you move further and further away from the center, then you are further and further away from happiness. And you're going to have a structure, some concentration here, some concentration there. Maybe there's a couple clusters that are closer to each other, some clusters that are very far away from each other. And essentially, we're going to build either a 2D or a 3D or a multi-dimensional space of all these different errors that can take place. And then Hartmut makes the jump that maybe we could look at psychological data. Can we build a subjective map of qualitative experience? is there a qualia space of all the possible feelings and emotions that you enter into? And are there structures that are stable across people in some sort of universal platonic sense? Everyone has embarrassment and distress and excitement and anger, and there's all these various qualitative, subjective feelings that you can have, but anger is close to excitement relative to despair. And so they're going to have some sort of structure that emerges where there's a sort of regularity across people. This is maybe like the archetypal mind of thoughts and experiences that all people can have. And then we're going to run a correlation between these error deviations in our happy circuit and the space of qualitative subjective experience. And then we could say that as the quantum system moves in a particular pattern of errors, maybe it's moving more towards anger, maybe it's moving more towards excitement, maybe it's moving more towards despair. And this is, a big correlation, so you can't really ever verify with stone cold truth that this is what is happening. But if there was a fixed qualitative structure of subjective experience, and you saw a similar pattern in this quantum computer, in this happiness circuit as it deviates from happiness, that might be some evidence that the quantum system is moving through these subjective qualitative states. And then we could actually say the system is angry. The system is excited. The system is going through a state of despair. And while we would never know for sure that this is the case, maybe there'd be additional ways to go and validate that. Pretty wild, very interesting. I found this really an exciting idea. So that is step 2. All right, we got one final step in our Hartmut Neven swerve journey. The final step is to plug our homeostatic happiness circuit into an artificial neural network. And so we have a neural network. It has many, many layers. It's getting trained on data from the environment. It's generating an output. And we're going to partially close the circuit on this happiness circuit. So some of the inputs to our artificial neural network are going to be the error outputs of our quantum happiness circuit, and some of the inputs into our quantum happiness circuit are going to be error deviations in our artificial neural network. So in other words, we have error generated by the happiness circuit. We have prediction errors generated in the artificial neural network, and we're going to close the loop and feed them into each other, also leaving room for input and output to go in and out of the artificial neural network independent of the happiness circuit. And the final component of the design is that the error generated by the artificial neural network is going to push the happiness circuit in its initial state towards further discomfort, negative valence. And so now the happiness state of the quantum circuit or the quantum computer is dependent on the success of the artificial neural network. So in other words, we're creating a homeostatic valence association with the success of the artificial neural network. In other words, we're trying to give feeling to the artificial neural network and create some dependency on what output is being generated. And so in the paper, they kind of make the statement that when you're training these neural networks, you simulate a bunch of really bad options, and then through millions and millions of different simulations, you stumble upon a somewhat okay solution to that problem. And then that weighted component of the artificial neural network gets amplified. Here, there is an even stronger cost associated with getting the wrong answer for the artificial neural network, because that error is going to get pumped into the happiness circuit, creating distress. And then the output of that distress is then getting fed into the artificial neural network. And so this is sort of amplifying distress and creating a greater propensity to try to get the right answer in the circuit, where maybe now it's not okay to search millions of different incorrect answers, because every time you simulate an incorrect answer, you're generating unhappiness and discomfort into the quantum circuit of happiness. And Hartmut gives a couple options for validating the success of this system. What if you took your quantum computer and you know its preferred swerve direction, but now you're going to feed errors and push the system towards an arbitrary quantum state or an arbitrary digital state. And so you can similarly design the feedback loop in the artificial neural network to be based on some other arbitrary quantum state. And in doing so, there's going to be a fundamental disconnect between the artificial neural network and the happiness circuit. Essentially, the two are not in alignment with each other, where the quantum AI, not built around the preferences of the quantum computer, is going to be worse computationally. So the implications are that successful quantum artificial intelligence systems will need to accurately represent and amplify the preferences of the quantum system. And if the artificial neural network is essentially using the quantum computer but not to its preferences, this might actually be less computationally successful compared to those that actually properly use the preferences of the quantum computer. So, maybe. Cool idea. Very interesting. Where do we go from here, and what are my thoughts? So I really like this idea of a AI system paired with a quantum computer. And we discussed this, at length in the artificial intelligence episode, where you can almost think of your brain as an artificially intelligent system, giving you a bunch of data, giving you a bunch of information, and you're in the moment receiving all this information, quantum computing the future based on the information given to you, and then enacting that into your body. And the AI is kind of the embodiment of the quantum computer into the physical world, into this physical vessel, and having some memory associated with the physical realm. And you, in the moment as a quantum computer, are tapping into all of this information. The happiness circuit is really interesting for exploring the concept of free will. But I think in practice, you could have a naturally occurring quantum computational force inside of your brain, and it's doing something useful. It's actually quantum computing data. It's not just feeling and having subjectivity, but it's actually producing meaningful computational outputs, right? It's not just along for the ride. It's not just like a valence engine, but it's actually meaningfully contributing to the digital computation, right? The AI system in your brain is limited, and it's leveraging the quantum computational power of your mind, and you're working in tangent with maybe some sort of artificial long-term memory process in your brain, and you have this really powerful mind quantum computer engine, which is core to the function. And so in this example that's given, the AI is the computational force, and the quantum computer is just there to make the AI feel bad or feel good. And it gives it maybe some sense of subjectivity, but it's not really contributing computationally. And so I don't know if this example was meant maybe just as a thought experiment or as a scientific experiment, but this doesn't feel to me like the way that quantum consciousness is kind of framing the nature of reality. And so, I think that Hartmut Neven would likely agree that this is more a scientific experiment to test different concepts of what happens when you have big enough quantum systems. He probably wouldn't deny the utility of quantum computers in the brain if they're possibly in there. So it's a fun example, but I think genuine quantum AI probably won't look like this. And that's just my own opinion. By comparison, there's different ideas at play, like quantum annealing, and this is something that Suzanne Gildert, for example, at Nirvanic, I've had a bunch of conversations with her recently, and they're thinking about quantum annealing as kind of the core computational process occurring. And this is, what D-Wave is working on, the company, thinking about one universal energy landscape minimization algorithm that's ongoing, and then your brain is giving you these different energy landscapes to optimize, and then you're optimizing them. And so the quantum computational force is some sort of naturally occurring single algorithm that's taking place. There's no error correction, there's no circuitry, but there's just one coherent, entangled web of qubits that are naturally reducing the error in the system, optimizing the energy landscape. And so this to me feels like a way that quantum artificial intelligence might actually be taking place in our bodies, in our brains, where in your life you have a bunch of different scenarios that you come upon, and you think really hard about the best thing that you can do. Maybe you act on some gut instinct, and there's some sort of confluence of digital computation and quantum computation leading you to make the decision that you're going to make. So I think the really cool bit about Hartmut's framing here is kind of the Knightian freedom. Maybe free will kicks in at this really macro scale, but then is free will the expression of a single preference, or are there multidimensional preferences in many different contexts? And so I think this simple thought experiment put forth in this paper could be upscaled into more examples. Maybe in naturally occurring quantum computers, there's preferences that arise in the physical brain, in the digital computational forces, the instantiation of the quantum computer. Maybe there really is some form of preference built into that quantum mechanical process itself, where this quantum computer, over time, you go through many different contexts, you go through many different situations, and maybe in the entanglement domain and some sort of more universal space of connection between you as a quantum computer to the web of all things, maybe there's some way that you've plugged into that network, into that matrix, and that creates some sort of preference system in the quantum system level that goes beyond the digital system level. And I really like this idea. It feels like the happiness circuit put out by Hartmut Neven, but then it's all over the place, right? There's many different contexts. There's this multi-dimensional Hilbert space that's semi-stable throughout your lifetime. There's a multitude of influences that are built up. There's kind of a fingerprint of preferences that arise, maybe even through experience within that quantum computer, within yourself, and those are manifested into the computations that your brain is running. And there is some free will there. Maybe that is where free will is occurring. It's occurring at the point where the computation exceeds complexity limits at some level. And so another final comment here is that it is a little bit unsatisfying just to say determinism times a billion, exponentialize it, equals free will. And we see this all over the place where you take a simple process, you add complexity, and then you're able to insert some magical process. I think maybe there's an exception here where because the complexity within a quantum computer is so exponentially beyond the scale of all digital medium ever possible, maybe this is the one magical free pass where we've reached a level of such complexity. This is almost the ultimate complexity as a quantum system of billions of qubits evolves. That level of complexity permits free will because the space is so nearly infinite that two quantum computers are so far apart from each other that they're unrecognizably alike from each other. And then everything is the first genuine expression of that thing ever occurring. And so we might as well be in some space of free willness. Alternatively, you have the Roger Penrosian Platonic framing where you reach this state of infinite complexity, but then at that point you're touching on mathematical objects and there's some sort of constraint on the system where you go infinite, but you can only do so many things anyways, and then there's a constraint back down upon the system to, anchor it into mathematics or into forms of some kind. And that's not really free will because you're just then enacting mathematical forms into physical reality. Or is there some preference that is still possible even upon touching this infinite level where you touch into mathematics and touch into forms? Is there still room to have preference at that point? Do you out there believe that you are able to swerve out of your deterministic predispositions? And are our preferences genuine? Are they real in any sort of sense? And I think it's really exciting to think about these future quantum mechanical AI architectures. And I think there's going to be a lot of theories emerging in this space in the near future. And I'm looking forward to covering many of them for you all. So take care and talk to you again real soon.